Here's another example of an application of Taylor series. So in statistics, you might have heard that this particular function, f of x equals e to the minus x squared, turns out to be a very important function. Briefly, the reason is because if you graph this function, you get the famous bell curve, and areas under this curve correspond to probabilities for normally distributed random variables. Anyway, it's very important to know what areas under this curve are. And areas under this, say, from x equals 0 up to x equals 1, for example. Well, we know that areas under a curve are just integrals. So the area under the graph of f of x from x equals 0 to x equals 1, that's just the integral from 0 to 1 of e to the minus x squared. But this integrand, e to the minus x squared, this is a very bad integrand. It's what's called nonelementary. It's a nonelementary integral. And what that means is there's no formula you can write down for an antiderivative of this function. If you try to write down a formula with powers and exponents and products and trig functions and logarithms, you will not be able to find such a formula whose derivative is e to the minus x squared. It turns out it's just impossible. So what can we do? If we can't find an antiderivative for this function, we aren't going to be able to use the fundamental theorem of calculus to evaluate this integral. Really, the best we can do is use some sort of approximate method for evaluating this integral. Something like the trapezoid rule or Simpson's method, one of those kind of things. But those methods have drawbacks. The main drawback is if you calculate an approximation for this integral, and then you decide you want to improve your approximation by, say, increasing the number of trapezoids in the trapezoid method, you would have to completely start over in your calculation. You could get a better approximation, but you have to completely redo all of the work that you did up to that point. And that is a serious pain. But now that we have Taylor series, there is a better way to go about approximating this integral. Since there's an exponential in here, you might think, well, why don't we replace e to the minus x squared with its Taylor series? And that would be an excellent idea. So the Taylor series is for e to the minus x squared is the sum from k equals 0 to infinity of minus 1 to the k over k factorial times x to the 2k. And we're going to integrate that from 0 to 1 dx. All right, and as usual, and somewhat mysteriously, we are going to move the integral inside the sum. So sum from k equals 0 to infinity of, we can also move the constant outside the integral, so minus 1 to the k, whoa, minus 1 to the k, there we go, over k factorial times the integral from 0 to 1 of x to the 2k dx. This is the sum from k equals 0 to infinity of minus 1 to the k over k factorial. Okay, now we have to do this integral. This is going to give us 1 over 2k plus 1 times x to the 2k plus 1 from 0 to 1. And now we need to evaluate at our bounds. So sum from k equals 0 to infinity of minus 1 to the k over k factorial times 1 over 2k plus 1. And now let's plug in our bounds. let's see, when you plug in a 1, you get 1 to the 2k plus 1, and 1 to any power is 1, minus 0 to the 2k plus 1. We have to be a little careful here because if we ever ended up with 0 to the 0, that would be a problem because 0 to the 0 doesn't make any sense. But this exponent, 2k plus 1, it's always at least 1. So 0 to the 0 never actually happens. We're always getting 0 to some positive exponent, and that's always 0. Okay, so the final result for that integral, remember this is all the integral from 0 to 1 of e to the minus x squared dx. The result that we get is the sum from k equals 0 to infinity of minus 1 to the k over k factorial times 1 over 2k plus 1. All right, now, so this integral that we wanted to figure out, we figured out it's equal to this series, but we don't know what this series is either. Using the ratio test, we could prove that it converges, but what does it converge to? We don't really know. But we can approximate what it converges to by, instead of calculating the entire series, just calculate a partial sum for the series. So instead of going all the way out to infinity, we could take the sum from k equals 0 just up to, say, I don't know, how about 3? Minus 1 to the k over k factorial 1 over 2k plus 1. And this would be, let's see, if we plug in k equals 0, we get 1 over 1 times 1. And then when k is 1, we get minus 1 over 1 times 1 over 3 plus, and then when k is 2, we get 1 over 2 times 1 over 5. And so this will be our third partial sum. Oh, sorry, we're going to k equals 3. So we need one more term. The k equals 3 term is going to be minus 1 over 3 factorial, so that's 6 times 1 over 3 times 2 is 6 plus 1 is 7. Okay. So this approximation, these are all rational numbers, so calculating this approximation isn't going to be too bad. And, you know, just going out to 3 terms, it's not a great approximation, but it isn't bad. And imagine improving this approximation. To improve this approximation, what you do is increase or go further along the sum, add more terms. Well, we already have the first 3 terms. To add more terms, we just need to start at the 4th. So we would add 1 over 4 factorial times 1 over 4 times 2 is 8 plus 1 is 9. And then the one after that would be minus 1 over 5 factorial times 1 over 5 times 2 is 10, plus 1 is 11, and so on. So by approximating this integral using a Taylor series instead of, say, a trapezoid method, we get to reuse all of this previous work. If we ever need to improve our approximation, we just use the approximation we already have and tack on a few more terms onto the end. So that's one advantage of approximating the integral in this way. There's a second advantage, which isn't so obvious, but it turns out that if you need to do this approximation to within a certain error, the Taylor series method gets closer to the real value faster than the trapezoid or the Simpson's method. This should be plausible given this sequence because look at how fast the denominators are increasing. There's a factorial in this denominator. So once you go out a few terms, these denominators get very, very small, very rapid. The denominators get very large very rapidly. So the terms that you're adding on get very, very small. And that means that after just a few terms, you're already very close to the final absolute value of the integral. So there's one extra bonus application for Taylor series.